All right, let's get started. Welcome back to ECEN 5817, Lecture 3. What we've been talking about so far are hard switching converters, and we looked at the losses in the hard switching converter in one of its transitions. Today we're going to complete that and then start looking at how we create a soft switching converter. All right, so a few announcements. Again, homework 1 just went out. It's going to be due by 10 a.m. Next Friday. Next Friday we have a guest speaker, not for our specific lecture. He's basically giving a seminar, but in order to sort of avoid me being tied up with this when we have a visitor or for a short time here, what I'm doing is I'm going to cancel the Friday regular lecture and move it up to Wednesday. So the 5th lecture, which would have been on Friday, is now instead going to be on Wednesday. All right. And just for those of you who are not on campus and don't know, Monday is a holiday, so there's no lecture on Monday. So 4th lecture will be at regular time on Wednesday, followed by a 2nd lecture also on Wednesday, except at 1 p.m. Same room on Wednesday. Okay. And then we have on Friday we have this guest speaker or this part of the seminar series, but I'm actually going to record it and make this available to the entire class. So if you can't make that time, or if you're a distance student, you'll still be able to see this lecture. Right? It's not part of our course, but it's just going to be a useful thing. So I'm going to add that as supplementary information. All right. All right, this is what we were talking about last time. The particular converter we had picked was essentially, looks just like a synchronous buck. And we were operating it essentially like a PWM hard switched converter. Right? What we did for that was we picked our L and C values such that the corner frequency of this this filter, this LC filter, was much lower than the switching frequency. So it essentially attenuated all the ripple, right? So your output voltage was fixed, and your inductor current ripple was small. Right? And in that case, what we found that we had energy loss or large energy going into the M1 device at the time when M1 was turning on and M2 was turning off. And then there was also some smaller amount of energy going into the M1 device when M1 was turning off. And last time we focused on that, and it actually turned out that that was not really a lot of energy loss, because that was really energy going into the output capacitors or capacitances associated with M1 and with M1. All right. So we looked at that transition, and that transition essentially looked like this. So this was M1 turning off. This was the transition that wasn't bad in the first place anyways in terms of the amount of energy involved. And better still, most of that energy was essentially going into charging of this output capacitance on M1. Right? So essentially it gave us 0 voltage switching or 0 voltage turn off of M1 and 0 voltage turn on of M2 without us doing anything special. We were just using the capacitors that were the output capacitances of the devices. And if the device was slow, like an IGBT, and we wanted to have the same kind of transition, we could just add more capacitance. Right? And it was really a game between how fast can the channel of the device turn off, right, versus how big the capacitor was. Right? So essentially you didn't want overlap between the current going through the device and the voltage rise across the device. Right? So the current was shifting off to the capacitors. Okay, so here's M1 transition and here's M2 transition, and both basically are lossless. Right? Okay, now let's look at the more tricky transition. Right, this is where we actually had a much larger amount of energy going into the M1 device, right? And we'll take a look and see where that energy goes and what is the cause for this. And we saw two things happening here. One was the fact that, let me pick a color. One was the fact that we saw a large current going through M1 when M1 was turning on, right? So this is at this is through M1, and then we also saw a large amount of energy that's going into M1. Right? So this is all related to M1. Okay. So let's explore that a little bit, and again, let's start with a simple model. First, let's ignore the capacitances. Let's just start with the two devices with their body diodes, and let's look at the initial state. So first of all, we're again going to assume in this case that our inductor current is constant. So IL is approximately some constant IL because we have a large inductor. And our initial state is that M2 is originally conducting, right? So the current is all going through M2, right? Because M2 is on. So we're starting with M2 being on, and at some point, so the voltage, let's plot voltage here. The voltage Vs, right, which is also the voltage across M2, we'll call that V2, that voltage is 0, right? So at this point, what I'm going to do is I'm going to basically turn M2 off, right? What happens? What happens when I turn M2 off? And remember, I'm not turning M1 on because I want to keep some separation. I want to keep some dead time to avoid short shoot through. So I haven't turned M1 on. Initial state is M2 is on, current is going through the inductor and M2, and I basically turn M2 off. Okay. So let's assume these devices are fast. I'm going to ignore the time it takes for the channel to kind of shut off. Let's say M2 turns off. What happens next?
It will become minus forward voltage for the D2.
Right. So where does the current go?
In the D2.
To D2, exactly, right. So the current is, so we start with this, and then the next thing that's going to happen is, because the current can't go anywhere, M1 is turned off, it can't flow backwards through D1, so the only place for the current to go will be through D2, right? And if you wanted to take into account the forward drop of D2, then essentially the voltage, this voltage V2, which is also the same as voltage Vs, is essentially going to become negative by the amount of the forward drop of D2. Right? So here now what we have is D2 just turned on. All right. Now, well, we can just stay in this state, but we really want to make a transition, so we have to now turn on M1, right? So let's say at this point, I'm going to go ahead and then at this point I'm going to turn on M1. Okay? So what's going to happen now? I turn M1 on. Let's sketch also. Let me see. Yeah, let's just also sketch the voltage across M1. So what was the voltage across M1? This is V1. Initially, M1 is blocking all of VDC, so you have VDC, right? And M1 is still off here, right? All right, and I am going to basically turn on M1. What happens? Well, let's talk first in terms of the currents. All right, M1 current is going to do what?
Take over. Increase.
It's going to go increase, all right? So I'm going to see M1 current, all right? So let's call this I channel 1, that's I channel 1. That current is going to increase, right?
Yeah.
And it'll increase at whatever rate it can go up. Let's see, let me just do this again. Let's also put a value for, let's say this is my IL, all right? So it's going to increase. What happens when it reaches IL?
Keep increase.
It's going to keep increasing. Can you tell me why?
Reverse recovery.
Yeah, because the diode was conducting current before, and so the diode still is going to look like a short circuit until I pull all the charge out of the diode, right? And so the current in M1 will essentially keep increasing. It'll increase to a point which is really determined by the parasitics of the circuit, the exact properties of this diode, any other sort of parasitics associated with the devices, right? So it's going to go above this, and essentially it's going to keep going until the diode is able to recover, right? And so this current will eventually come back down, but it will have to go up and incorporate this entire area, which is the reverse recovery charge in the diode, right? So essentially has to pull all of the reverse recovery charge of the diode out, and then it can become equal to IL, right? So that's what it's going to look like. All right, now what is happening to the voltage across M1? So the diode is still on throughout this period, all right? Let's call this period the reverse recovery time. So this period here is the reverse recovery time of the diode, and through this time the diode is still on. So the only thing that can hold up voltage then is the MOSFET, right? So the voltage is still appearing across M1. Right?
Yes.
This is our V1, and once the diode is basically able to block voltage is when the voltage across this diode can rise, right? So throughout this period we have essentially the diode conducting, and then the diode voltage can go up. And what I'm going to make an assumption for this is that it's a snappy diode. What a snappy diode basically means is that once all the charge is removed, that's basically it just snaps back up and it blocks voltage immediately, right? So in the snappy diode, the voltage will then just sort of quickly come up to the VDC level like that, and soften that corner. That's the voltage V2, right? That's our V2 voltage. And basically this voltage is then able to, right? Again, the sum of these two voltages must add up to VDC. Okay, so that's what happens. Now, do we have loss? Which device has loss?
M1.
The MOSFET. M1 has loss because you have voltage and current at the same time, and we can calculate that loss. We'll call this energy. First, let's just calculate the energy that goes into it. We'll call that E on. And E on, essentially, you can calculate by multiplying V1 with I channel 1, right? Or integrating. So it's essentially V1 times I channel 1 dt over this time period, 0 to TRR, and we can write that simply by breaking this up into two integrals, right? One is basically you have a current of roughly IL times this voltage VDC, right? So I have my first thing is just going to be VDC times times IL times TRR, right? That's essentially going to be this area here, right? I mean, basically this piece of the current multiplied by that voltage, right? And then the second part is going to be VDC times QRR, right? QRR is already the full area of that current, right? And so you can then calculate what your power loss is. The loss in this transition, in this switching transition, is essentially going to be E on times your switching frequency, right? And this is really loss during on M1 during the turn on transition. So maybe all this turn on transition loss. Okay. What about the loss in the diode? Is there any loss in the diode? The diode is essentially carrying current. We wanted to draw the diode current. Previously, the current was in M2, and the M2 current came down, but I'm not going to sketch that. The diode carried current equal to IL here, and then that current, sorry, that's actually not true, because the diode current actually went negative. So I'm not going to plot that, because I'm actually going to give that to you as a homework problem. But you can see what the diode current would be, because the diode current plus this current has to add up to the inductor current, right? So I won't spend time. But you can see, because, I mean, there's going to be some small loss in the diode, but most of the loss is essentially, in this case, in M1, right? Now, this is the case of a snappy diode. The snappy diode is sort of the worst case for M1, because all the loss happens in M1. In general, the diode is not going to be ideally snappy. It's going to be sort of somewhat less ideal than a snappy, and so there will be a sharing of loss between the diode and the MOSFET. In fact, when there is sharing, you find that actually the total loss turns out to be slightly less than in the case of the snappy diode. All right. In fact, you're going to get this all for a homework problem, so I'll let you work this out there. Let me just also point out that, I mean, I ignored the capacitors here, right? What happened if I now include the capacitances in this model, right? So I've ignored capacitances for now, and in fact, I'm not going to do that problem because it might make for a nice another homework problem. But let me just talk you through it. Suppose I did put capacitors here. Does that help in any way? Right? In reality, we will also have capacitances. I didn't solve you that problem yet. So if I include the capacitors, so I'm going to put that, say, this. So suppose I do have C DS2 here, and I do have C DS1 here. Okay, how does that modify anything? First of all, do you think it will help?
It should help.
I'll take in one more guess.
Slow the voltage rises and drops, so slow the transitions.
Well, change the transition shapes slightly, but a yes/no answer on do you think it helps or hurts?
No. No.
Helps or hurts?
It hurts.
Hurts. All right. So one side helps, one side hurts. It actually hurts. All right. So first, think about it. So in the beginning, if you had this, when you started this transition, right, the current would shift from the MOSFET, let's say, to CDS2, right? As soon as, so what it does to CDS2 is it discharges it more, right? As soon as the CDS voltage, the negative voltage becomes enough to forward bias the diode turns on. And so the CDS voltage isn't going to change anymore, right? So you're back to the situation where the diode is conducting, right? Not much changed really. Then when you go to turn on M1, right? And remember, in this time period, you have both D2 plus M1 on, and then this is where you just have M1 on. Right? So when you go to turn on M1, what's the initial condition? You have this capacitor charged up to the full voltage. This capacitor is close to 0 voltage, in fact it's negatively charged, right? Now the current that goes through this M1 is, in addition to the current that was going to do the reverse recovery, you have the current that will flow because of the discharging of this capacitor. It also goes through the channel. Plus you need the current to charge up this capacitor. So the discharge of this capacitor and the charging of this capacitor, the current required for that, also goes through M1, beats up M1 even more. So you actually get hurt by the fact that you had the CDS1 and CDS2. So when I said you have a slow device, you can add more capacitance, well, that doesn't come for free. Okay? It helped you in that transition, but it hurts you now in this transition. Right? So nothing is free in this world. Right? So that's the kind of thinking you will be kind of become really good at as this course progresses, because you'll look at this and you'll say, okay, should I add capacitance here? No. Maybe I should, maybe I shouldn't. This is what's going to happen. Okay. So this is the kind of stuff that will now start to take us beyond intro to power electronics, because you're going to be able to figure these things out quickly. I want to say a few words next about the diode, because you're going to have a homework problem where you'll actually be solving similar kind of a problem, but not a snappy diode, but a sort of a soft recovery diode. Right? So snappy diode is where you essentially, as soon as you remove the charge from the, or you've kind of reached the point where the junction can start blocking, it essentially all the charge is gone, and suddenly the voltage will rise across the diode. Right? But in a sort of a more realistic diode, you're not going to have that kind of a snappy behavior. So what's shown here on this slide is essentially something out of a diode data sheet. And what it shows you is basically the results of a test done on a diode when the diode is being turned off in a circuit which actually is very similar to the circuit that we were just looking at, right? Except it doesn't have all the paraphernalia, but it has a device that's turning off while the current before that was running in this diode, right? And there is the inductor. So the inductor current is going through this diode, and at the same time you're going to turn on this device, and so you're going to see that reverse recovery through this diode, right? Essentially it's the same circuit, just things are kind of backwards. The diode is above and the MOSFET is below, but nothing else different. Okay, so what you will then see is that this was the current through the diode in the beginning, and then the current will kind of flow, will decrease because the current is now being picked up by the MOSFET. But the current doesn't stop at 0, as we know, through the diode. In fact, it goes negative until you've pulled all the charge out of the diode. And then at this point, at this sort of where you see this little knee right here, that's where the diode starts to block voltage. Right? Basically now it starts to recover, and then the current will sort of decline. In the case of the snappy diode, essentially the current goes up to here and then just snaps down to 0, right? And the voltage essentially just snaps straight up. In this case, the current profile will look more like this, and for the homework problem, you'll just approximate it as a triangle, right? So you'll basically assume that this is a straight line down, and then this is a straight line there, okay? So by definition, a snappy diode is where this time TA is much, much greater than TB, right? So you can basically ignore TB. And then in a soft recovery diode, and you can buy diodes of different characteristics. the time TA will be of the same order as the time TB, right? And that's kind of the problem you will be doing in the homework set. All right, now, if you were really wanting to get into this, what you will find is that these parameters, the important parameters for a diode, are the total charge that you have to remove, the reverse recovery charge, okay? The peak current level that you go to when you are sort of recovering the diode, and the time it takes for the diode to recover, TRR, okay? And in data sheets, you will get values for all of these, but they will be dependent on a number of other parameters. So the parameters that they depend on, most importantly, are what is the initial amount of current going through the diode. They depend on how fast you reduce the current through the diode. So it depends on the slope as you're going through the zero crossing. And it also depends on the temperature, all right? So if you went to a diode data sheet, you'll find charts like this. This is just giving you an example here. And so, for example, if you look at this chart, this is plotting the reverse recovery charge. And as a function of, for example, the rate at which you turn the current off through the diode, this QRR varies, okay? In fact, if you try to turn the diode off very quickly, QRR actually increases, the reverse recovery charge increases. The reason is because if you're trying to turn it off very rapidly, then you have to pull all of the charge out of the diode. If you do it more slowly, the diode has time for the charges inside to recombine, right? So not all of the charge has to be pulled out. Some of it can just recombine inside the diode, and so it reduces the QRR which you actually pull out. If you have higher temperature, then you will see that you have more charge in there because at higher temperature there's more charge, and so QRR goes up with temperature. So these dashed lines correspond to higher temperature. And then the other thing that's shown here is how it depends on the initial value of the current. So the initial value of the current is higher, you have again more charge in the diode, and it takes long, so you have to pull more QRR. QRR goes up, right? The other factors are also similarly related, and it all makes logical sense, but they are fairly, the relationships are fairly nonlinear and complicated. Right? If you're interested, you can kind of look into this. All right, I'm going to move on now to how do we, given that we have this reverse recovery issue in diodes, how do we use circuit techniques to reduce the loss in our circuit, right? And that essentially brings us to soft switching, right? So this is again the same circuit that we had before. This is the same thing that was our synchronous buck. And I'm going to make one small change, right? Just one small change. And that small change is essentially that I'm going to change the value of the inductor. So previously we had a 100 microhenry inductor here.
Henry. Oh.
Yeah, we had a 100 microhenry inductor here before, and I'm going to change that, reduce it by a factor of 10 to 10 microhenries, right? Nothing else has changed, everything else is the same, okay? What that does is it changes our corner frequency, now becomes 16 kilohertz. Before, I think it was, let's go back and see what it was probably 4 or 5.
50s? Oh, fine.
It was 5 kilohertz before, right? And this is where you had the 100 microhenry. So we've changed that to. So what do you expect? For example, what do you expect would be the change in terms of the inductor current?
Larger ripples?
Yeah, it'll have larger ripple because you have a smaller inductor. What do you expect would happen at the output, to the output voltage?
Maybe it does not change much.
Yeah, it's not going to change substantially. It may be slightly higher ripple, but the capacitor is still pretty large, right? So the big difference is that our inductor current ripple is going to be larger now. All right. So we expect larger inductor current ripple. All right. So let's simulate this circuit and see what happens. All right. Here is the simulation. Again, you have first M1 on here, and then you have M2 on. The switch node voltage looks just the same as before. Here's the difference that we expected, that the inductor current has higher ripple, right? It's still, the average value is still 20 amps, right? But the ripple is considerably higher. In fact, probably 10 times higher, because we have a 10 times smaller inductor. The output voltage has slightly more ripple, but not appreciable. I mean, it's still fairly flat. But what's the big difference here? Look at the power, right? We used to have large spikes at the transition when we were turning on M1, right? So when we turned on M1 here, right, from the transition from M2 to M1, that used to be a big spike, power spike is gone. What happened? Ooh, magic. Right? I just changed the inductor value. I just changed it from 100 microhenry to 10 microhenry, and you have no power spike. That was the problem, right? That was the big loss. That was the diode reverse recovery. If we add capacitors, there's capacitor discharge and charge loss as well. All of that's just gone. Here's what you have to notice, right? The big difference is not the fact that you just have large ripple, but the big difference is that you have, at that transition, negative current through the inductor, right? So here's your 0 amp level. So that transition is now happening with negative inductor current, okay? So let's look at that transition again and see what would happen if the inductor current was actually negative, right? I'm going to still assume that IL is approximately constant through that transition, right? So it's not going to be, obviously it has a large ripple, so it's not, but I'm just going to assume that it's approximately constant during this transition. That's a good enough approximation. That transition happens pretty quickly, right? And so the current, however, now IL is negative, so it's actually flowing in that direction, right? Because my IL is now less than 0. And so the state that I'm going from is M2 is on, right? And so the current is now actually flowing through M2 in this direction, right? That's my beginning state. And so what I'm going to do again at this point is I'm going to do M2 turn off. I'm going to just turn M2 off. Okay? Now where does the current go? Again, I'm going to ignore the capacitors. Initially, I'm just going to add back the capacitors. But where does this current go now?
D1.
Goes to D1. Yeah, it doesn't go into D2, right? Let's now, that's exactly what's going to happen. Eventually it's going to get into D1, but let's now add back in the capacitors and just kind of do the real problem and see what happens with these capacitors. So here's CDS2, here's CDS1, all right? So now it won't immediately get into D1. What sort of the intermediate step, right? So I turn M2 off. There's no place it can go into M2. It can't go into D2 because that would be going in the backward direction. M1 is still off. So it can either go into D1 or it can do something with the capacitors, right? So D1 still needs to be forward biased. It's initially, the voltage is all being blocked across this device, right? So this voltage V1 is initially starting off with VDC, right? So D1 is reverse biased, so it can't immediately conduct. You have to somehow get it forward biased. And this V2 here is sitting at initially 0 volts, right? So what happens? What does the current, where does the current go? What's step 2?
Charges.
Yeah, it goes into the capacitors, exactly. It's kind of the opposite of what we saw in our earlier transition. And basically it discharges CDS1, right? And discharges it down to 0 volts. And it charges up CDS2 up to VDC. It's going to, again, this is going to go more negative than 0, enough to sort of forward bias D1, but I'm going to ignore that, and this will then go slightly higher than VDC. But at that point, then D1 will turn on, right? So if we looked at voltages, so let's look at voltage across M2, V2. So initially, it's going to charge up capacitor 1, and I'm also going to ignore that slight period, the amount of time it takes for the channel current to go to 0, right? Just going to ignore that. That's a pretty short time. So so the current just splits, starts charging these up, so that this voltage will rise, all right? And we're assuming that the current is constant during this transition, so it's a constant current charging the capacitors to first order. This will be a linear rise, and the voltage on V1 will come down, and let's say this was VDC, and that was VDC, so that essentially comes down, and that's what happens, right? Now, if you wanted to be really accurate, this obviously is going to go slightly negative, right? So it might actually go a little negative, and this would actually go a little positive, and this is the point where then your again, we wanted to do this right, no device conducting, and then here you have D1 conducting, right? So now, once D1 is conducting, we have the opportunity to turn on M1, right? And it has no voltage across it. It's essentially 0 volts, right? So then I can just go ahead and turn on M1, all right? And if I do that, then essentially I have 0 voltage turn on of M1, right? So if I wanted to plot the current through M1, the current in M1 will pick up here. So no current, and then I'm turning M1 on here, so M1 current rises up and goes to IL, right? To be proper, this is little IL, okay? So, make sense? So again, I have been able to achieve 0 voltage switching of both my devices and get rid of that switching loss. How cool is that, right? Because this circuit is so good, it actually has its own name. It's called the 0 voltage switching quasi-square wave converter, right? And essentially a buck-derived converter or a synchronous buck-derived converter. And we'll talk a lot about this later on, but I just kind of throw out the name here. Okay?
How about the current of M2?
Well, current on M2, we turned M2 off.
Also, it becomes there.
So the M2 current was here. This is I channel 2, right? This is I channel 1, and I channel 2, I just assumed it went down to 0 quickly. In reality, there's some slope, there's some quadratic period. I'm ignoring that, right? So that's what you have.
Will there be any small power loss because of the diode conducting?
Yeah, so there will be some small diode loss there, and if you wanted to be really accurate, this would not come down like that, it would actually come down like that, and the voltage waveform here would actually kind of have this quadratic period and then the linear rise period, right? The same thing we did earlier. I did it much more carefully here. I'm just kind of ignoring ignoring current fall time of M2. Okay, and then by ignoring it, it becomes that one, right? But yes, there'll be small loss, and in fact, if you look really carefully on a sort of a more minute scale, you'll see some loss there. By the way, I've uploaded these LT Spice files in additional learning material. You're free to download and play with them. Right? It's not a required part of this course, but if you want to, you have them. Okay, let's then make one more change, and I'm going to go a little faster. So last time what we did was we simply reduced the inductor value. Now I'm going to use the lower inductor value but also change the capacitor value. Right? So the capacitor value is now also reduced. We had the capacitor value previously was, I think, 10 micro. So I've gone from 10 microfarad to 0.5 microfarad. Okay, what do we expect now?
You have a lot higher voltage ripple.
Yeah, you're going to have a lot higher voltage ripple, and because the voltage is no longer going to be on this side constant, the current in the inductor may no longer look triangular, right? Because the triangular basically assumed you had constant voltage across the inductor, and so you had sort of straight ramp up and ramp down. Okay, let's simulate this and see. All right, again, we have our transitions, M1, then M2, then back to M1. Again, switch node voltage looks as before. Here is the inductor current. And as you can see, it's no longer triangular, but it has large ripple. You would expect large ripple. The voltage at the output also is no longer constant. It has very large ripple, and it looks sinusoidal, right? And you can kind of expect that. You're putting in a square wave into an LC tank, and the LC tank has now a resonance frequency very close to your switching frequency, right? So essentially what I was putting in here was a 50% duty ratio square wave of frequency 100 kilohertz, right? And if you put it in a resonant tank which has a sort of a resonance frequency close to the switching frequency, well, it's going to keep that fundamental, it's going to attenuate away the higher harmonic, so it's going to basically take the square wave and kind of keep its fundamental, smooth it out, essentially. And that's what you're seeing, right? Basically seeing a smoothed out version of that square wave, but the average value is still 100 volts, right? Makes sense. And again, the key thing here is that I have negative current in the inductor at that transition, right? The transition from M2 to M1, which was the transition that troubled us, again has negative current, and so again that power loss is gone, right? Same phenomena, same everything, except waveforms are slightly different, but it's the fundamental thing here was that the current was negative. What you really have to actually have is enough energy in that inductor to be able to charge and discharge those capacitors, right? So it's not that it's negative, it needs to be negative enough that there is enough energy in that half Li squared energy to basically charge, discharge those capacitors. We'll look at that more carefully later. Okay, but same advantage. This is just zooming in to those transitions. This is the transition where you had M1 turn off. This was never bad anyways. It hasn't changed. It's essentially the same, right? You're still putting energy into those capacitors. And here, this is the bad transition. The problem is gone. The good thing now is that even though in that earlier transition you've put energy in those capacitors, now because the current is negative, it's actually discharging those capacitors and not wasting that energy in the channel of the MOSFET. It's either supplying that energy back into the source, or it is just part of the output current, right? In either way, it's basically it's not a this transition is really nice, right? The M1 turn on transition. But essential thing again is current was negative at that transition, the inductor current. Now let's do a comparison of efficiency between these three types of converters, right? By the way, this converter that we just did, where we decrease the value of the capacitor, is your first example of a resonant converter. And this is actually called a parallel resonant converter because the resonance that will occur is between this L and C, and this R is sort of in parallel to all of them, so this forms a parallel network, right? So this is, we will also see series resonant, but this is parallel resonant, right? So let's compare now the efficiency of these three converters that we have, and these are the results. Right? So let's start looking at them. So first of all, let's look at one of the devices. This is the upper MOSFET. So U1 includes the diode associated with M1, right? So that's what U1 is. So we start off with our hard switched, which had about 57 watts of loss. When we went to the zero voltage quasi-square wave, this was when we just reduced the size of the inductor, we reduced the losses, okay? But the losses didn't go down as much as we may have expected, right? We almost saw visibly no losses at that switching transition, but something else happened that we'll look at in a moment, all right? Let's look at the other device also, U2, which is the lower device, right? And that had even previously fewer losses, right? This is mostly in the diode, right? But those losses actually went up in this case when we did the quasi-square wave. So what do you think actually happened? Why have these losses gone up, and why have these losses not decreased as much as we may have thought? Right? Certainly switching losses, and I can guarantee you, switching losses decreased tremendously. Something else happened. Yeah, conduction losses. Because you now have much higher ripple in the currents. So the RMS current that's going through that device for the same amount of average power that delivering to the output is much higher. So your conduction losses went up. So this is always going to be a trade-off and a challenge for you to see as to how much ripple do you really want so that you maintain minimum amount of RMS loss while reducing your switching loss, right? And you see that right here. Overall, you do have an advantage in total losses, right? And in fact, in this particular example, the zero voltage switching quasi-square wave converter actually turns out to be the best out of all three in terms of losses. So here's our winner. Why do you think the resonant converter was not quite as good? It's better than the hard switching, but it's not as good as the quasi-square wave.
Conduction loss.
Same reason, conduction losses, because in here you have even higher ripple, right? And I should point out, it's not, mostly it is conduction losses, but there's one other factor, and that other factor is that there are the losses at turn off of these devices are now happening at higher current, again because of the higher ripple, right? So the device has to turn off a larger amount of current, and as we will see, how much current you turn off also determines how much switching loss you will have, right? I mean, we know it's reduced, but it doesn't go to zero, and the amount there is depends on that current that you have to turn off. So that's the other thing that's going on. We can also, I have a couple of minutes and that's all I need. We can also look at these converters under light load operation, right? So all I do here is I just change the output load, right? So instead of 5 ohms, I'm going to 50 ohm load resistor, and I'm just going to go and simulate those 3 circuits again, just with a under light load operation, right? And under light load operation, here's what you'd see with the hard switching PWM converter. it also has no big loss at that transition from M2 to M1. Why do you think that's true?
In her DCM,
Yeah, basically the average current has gone down, ripple has stayed the same, so at that transition which was troublesome, even the hard switching converter now has negative current, right? So no new phenomena, it's the same old phenomena. It just happens that at this operating point, with already the inductor size, the ripple was large enough to give you zero voltage transition even on the M2 to M1 transition. So, and in fact, if you now, this is the simulation with the quasi-square wave, you actually see that the return of the switching losses actually were lower in the case of the hard switching than in the case of the quasi-square wave. Again, because you have larger ripple here, so the turn off currents are larger, and just the thing I just explained, you will have higher losses in this, right? And then the resonant is even worse because it has even higher ripple, and so while it kind of reduces all the diode reverse recovery losses, but the turn off loss again is higher because you have higher turn off currents, right? And your RMS currents are going to be higher, so your conduction losses will also be higher. So just this is the final slide. If we compare these converters, right, we've already compared them for sort of full load conditions. Under the light load condition, it actually turns out that your hard switched converter is actually the winner. Right? While at full load, our quasi-square wave guy was the winner. And this basically highlights the importance of kind of picking the right topology for the right application. But more importantly, it raises the point, which is a fundamental problem with soft switching converters, is that you can design a soft switching or a resonant converter really well for one given operating point, but designing it to be highly efficient across a variety of operating points is the biggest challenge. And this course is going to teach you how to do that. So this serves as a motivation for, yes, we quickly were able to build a soft switching converter, but it isn't what we really want, and now we'll spend the rest of the course not just on this topology. We'll have lots of different topologies, but we have to start going back, look at fundamental principles, learn how to analyze these converters, figure out what's the best choice and how do you do that. All right? So hopefully this gives you some motivation for how to do this stuff. So that's why not too many people know how to do it, because like if you do it the simplest way, it's not always going to be working out the way you expect. Okay. So have a great weekend, and I'll see you all on Wednesday when we will actually have 2 lectures, and I will post the information about the Plex workshop as well. All right? See you all. Have a good weekend.
next shop is today.
What?
Next shop's workshop.
Oh.